Okay, so good morning, everyone, and welcome, and thank you all for coming. So on behalf of the organizers, I wanted to say a few words before we start the week. So it's customary to give thanks at the end of the week when you're really sure the conference was good. But I wanted to invert things a little bit, and I wanted to start by thanking all the people and institutions who made the conference happen in the first place. So first and foremost, the National Science Foundation, which provided a very substantial funding for the conference. MIT, they provided funding, but also a tremendous amount of logistical help. This is really a kind of joint endeavor with MIT. The Clay Mathematics Institute, and last but not least, Northeastern College of Science, where we are, and the Math Department. Now, about the conference, as many, all of you know, we're here to celebrate a very important event that happened 50 years ago in July 1969. And I'm not referring to the Apollo mission, by the way, but the fact that on July 26, 1969. Yeah, I was thinking actually if we called representations lunar modules, maybe we could ask for some funding from NASA. But anyway, that's fine. So on this fateful day, two very very important mathematicians were born the same day, who are in the room, and they have had and continue to have a tremendous amount of influence in the subjects that will be discussed this week and well beyond. So it's an enormous pleasure to have this conference to celebrate Pavel Lettingov and Andrei Okunkov, who last July collectively turned 100 and remarkably youthful for their age. And if I could offer a very small anecdote, I myself, since you've been out, I myself turned 50 last year, and I was complaining about this to a friend of mine who's a few years older, and I'm saying, well, I might be over the hill, and he said, oh, don't worry, beyond the hill is a very tall mountain. Okay, all right, so just a couple of logistical things before we do start climbing the mountain. There is, as part of the celebration, there is a conference banquet on Wednesday. The details are on the website of the conference, where you can find everything, hopefully. But you do need, if you want to come, you do need to register by today, 5 p.m. So it's a simple doodle poll, just tell us whether you're coming or not. It's a subsidized dinner, so grad students pay $20. All other guests are free of charge, of course, and then all other faculty pay $40. But please let us in the rest. In cash in the rest. Thank you. But please let us know today by 5 because we need to give the restaurant a precise head count. Second part of the celebration, Pavel himself organized a mushroom hunt. Actually, this is a mushroom, for those who were wondering.
So there will be an email about this.
Okay, there was an email, so please get in touch with Pavel about this.
Actually, there are very few mushrooms, so I'm afraid that it will be not much of a
Okay, well, we'll have to chop them very fine. And what was oh yes, the last detail is for those who are receiving financial assistance, there will be, or maybe there is already a link on again the web page for you to upload your reimbursement form and reimbursement material. Okay, so that's right. So I'm very very happy to welcome the first speaker this morning, Professor Hiraku, whom I have to hook up. And so our first speaker is Professor Hiraku Nakajima, who will speak about gauge theory with symmetrizers.
Thank you very much for introduction. So I'd like to thank organizers for kind invitation. It's great honor and a great pleasure to give a talk on this workshop on this special occasion. So happy birthday, Andrea and Pasha. Let's see where is. So I start with some general problems and case with symmetrizers. So let G be a complex, simple Lie algebra of type ADE. Then I assign three infinite measure affine Lie algebra. One is G hat 1. This is G1. This is untwisted affine Lie algebra associated with G. Then I consider the diagram automorphism. So this is the first one. So diagram automorphism. Choose and consider twisted affine Lie algebra. So R is the order of this diagram automorphism. And the third one is its Lagrange dual Lie algebra. So this is the Lagrange dual in the sense applied for the affine Lie algebra. So I take the Cartan matrix for the affine Lie algebra and take its transpose and consider Lie algebra, Kac-Moody Lie algebra corresponding to this Cartan matrix. So this is untwisted affine Lie algebra. Or of type A to N. So this A to N has this thinking diagram. Yes, this type of thinking diagram. And all the affine Lie algebra appears in this way. Should I keep this? Oops. Then there's some vague conjecture. I'm not sure who contributed to this, who gave this conjecture. So representation series of so I consider the corresponding quantum affine Lie algebra. And later I will consider that the modified version, which is called truncated shifted quantum affine algebra. So the conjecture is representation theory. Of three algebras. Somehow related. So I will make little more process later. So this is not so apparent because this twisted affine Lie algebra is subalgebra of untwisted one, but the simple restriction of the representation doesn't give this kind of relation. And then relation with Lagrange's real algebra is even more mysterious. But there are some evidence. So first is, maybe there are earlier ones, but what I know in the literature is the one due to David Hernandez in 2007. So he showed that there is a ring isomorphism between the Grothendieck ring of the finite dimensional representations of quantum affine algebra.
Is it Hernandez?
David Hernandez. I hope this Her. Her.
It's a twist of the part.
Nan. Her. I hope this is correct. So he considered the finite dimensional representation of UQ untwisted and K0 of the finite of the twisted one. And they say they are isomorphic. He constructed an explicit isomorphism. So the quantum affine algebra is a Hopf algebra. So its category with finite dimensional representation is a monoidal category, and it is known that if once you take the its Grothendieck ring, it becomes commutative. So this is isomorphism of two commutative rings. And
is it over the integers?
Yes, it's over integers and sending the so-called Kirillov-Techetsky modules of this untwisted to Kirillov-Techetsky modules.
So it is maps basis to basis?
Well, but the natural base is basis on simple modules, and it is not clear. But he just defined a ring isomorphism by sending KL. KL modules are a particular kind of simple modules, and they are not the basis. But they include the generators of this commutative ring. So it's enough to define its ring isomorphism. It's enough to assign the target of the Kirillov-Techetsky modules. Then this is the first. And then subsequently, Frenkel and Hernandez so this is 2009. So they proposed Lagrange's duality. Representation of finite dimensional representation of UQGR, twisted affine real algebra, and representation of UQ, its Lagrange dual. So unfortunately, this is not precise. What does Lagrange duality means? So there's no, as far as I understand, it doesn't have clear statement, but somehow this is based on the earlier observation by Frenkel and Reshetkin about this Grothendieck group has quantization given by the double algebra, and double algebra for this and double algebra for this has one parameter deformation, common one parameter deformation, which specializes to both of Grothendieck rings. So anyway, so there's some interpolating. And they express these interpolating objects as some deformation of Q characters. So they introduce certain deformation of Q characters, one parameter deformation of Q characters, which is specialized Q characters for this and Q characters for this, according to some specialization of the parameter in a different place. So this is what they observed. Then Kashiwara and his collaborator makes this correspondence much finer. Should I? I'm not sure how to use. So this is a little more recent. Kashiwara and O in 2017, and Kashiwara, Kim and O in this year. So they, because of some technical reason, they need to assume G is a D and R is 2. So they exclude R equals 3 case for D and exceptional groups. So representation of finite of UQ G of 1 and representation finite UQ G of R and representation of fine with Lagrange there. So all these three contains the same monoidal subcategory, and pitch is, sub-monoidal sub. So pitch is relatively large. I don't specify what I mean by large, but so that is the common piece is a representation of the Kähler algebras.
And this isomorphism restricts to identity map this subcategory?
This isomorphism?
Yeah.
Yeah. Identity, yes. Representation of Kähler algebra of type G. So this is also is equal to this Kähler algebra is the convolution algebra. This is convolution algebra of a Quiver of type ADE. So for which heuristic is to define canonical basis.
And what do you mean by monoidal subcategory? Is it closed?
It is closed under tensor product.
But not undertaking subclosure.
Yeah, it's also closed.
Closed
under. Yeah,
so it is determined by some
set of simples.
Subset of simples.
Some set of simples and generated by those. And they constructed those functors by using what they call the shear wire duality, generalized shear wire duality.
So this is a Serre subcategory.
Serre subcategory, yes. And using the delimitating, they see that these Grothendieck of these having the structures of cluster algebras. And so this is some interesting development. So today I'd like to propose a geometric approach to understand these to this problem. Geometric, I mean using Quiver varieties. So, Quiver varieties is defined for symmetric quiver in particular. So for finite type case, we can consider Quiver variety for type ADE, but until recently, we didn't know how to modify this Quiver variety construction to other affine Lie algebras. So today I want to propose some modification of this previous construction. And also, we can also talk slightly different, but I hope this is similar problem. Also, some category of possibly infinite dimensional representation of truncated shifted quantum affine algebra. So unfortunately, so this is related to the quantized Coulomb branch, which is again some geometric construction based on the convolution algebra. So this think about symbolic show that this quantized Coulomb branch for type A is isomorphic. I mean, there's some technical points. They don't really show that isomorphic. But so anyway, so this quantized Coulomb branch for type A is related to truncated shifted quantum affine algebra, and this is supposed conjecturally to be generalized to other types also. And their representation theory can be also understood using geometry of the variety which was used to define Coulomb branches. And there's a modification to cover the quantum affine algebra of untwisted, so this Lagrange diagram, so which I recently worked with Alex Ruiz. And
so can I ask?
Sure.
So irreducible representations are parameterized by highest weights, which are Greenfield polynomials. So you said that there is a subcategory. So for example, in the untwisted case, can you say which Greenfield polynomials?
Yeah, so I cannot say right now, but there is
explicit.
This is explicit. I said I think that the person.
Poisson-2 is just one polynomial.
And the basically the interesting one is the case when the pole of the polynomial is powers of Q, yes. And I think they only consider the positive powers of Q, something like that. So, but essentially, I mean, once you know the representation theory of the positive powers of ones, then you basically by the automorphism of the quantum affine, you know all the representation. In that sense, this is large enough subcategory.
R. Positive powers of Q.
Yeah, something like that. I
So
vaguely
it is not
remember.
closed, this category is not rigid. It is not closed under taking tools, right?
No, that is not. Yeah, that is not.
Okay. So it's maybe closed under right tools, but not left tools, something like this.
Even that, I think it's not close under these details, but someone could correct me. So I approach to this property in 2 steps. So step 1 is modify the constructions UQG of R1 to other cases representation. Then step 2, so analyze representation theory. Using techniques of Quiver. So this is, as I said, this is a convolution algebra. So you can use his technique to analyze the representation theory. So in particular, it is important to understand compute. It is important to compute fixed points sub-variety in either Quiver varieties or maybe I should say this quantized Coulomb branch is a case area, equivalent case area or equivalent homology of variety of triples, which I will record the definition later. Then to analyze the representation theory of modified setting, so we also need to study Quiver variety or a variety of fixed point subvariety in variety of triples. Then, at least in the case which I studied with Alex Wicks, so the fixed subvariety in variety of triples are the same for this setting and this setting. That is the geometric reason why the representation theory are the same.
Fixed point of what?
Fixed point in Quiver variety of fixed point in variety. Fixed point with respect to one parameter subgroup.
If R equals to 1, then you have just G1 and Langland's dual of G1, yes? If
What
R
do you say?
equals to 1.
R equal 1.
R equals to 1, this doesn't apply.
Well, R equal 2 or 3. So they by some technical reason they exclude R equals 3, but they expect the same is true for R
But for
equals.
R equals 1, this is, you don't get two different subcases.
No. R equal 1. What do you mean? R equal 1 case, this part disappears and just they understand. Alcohol. One case, this is contains some monoidal subcategory which is same as the category of KLR algebra.
So LG is isomorphic to LG1 is isomorphic to G1, and you get the same. You don't get two different.
No. In that case, I exclude. I don't consider so. Maybe sometimes yes. I may consider the diagram automorphism, but anyway, I don't consider. Any other questions? Let's see. Do we have a better eraser? No. This is the only eraser. Okay, I started with the twisted case. And this has been proposed by Rick Basel many years ago, but somehow I feel that somehow foundation for the twisted affine algebra is not settled at that time, so I postponed to study. But anyway, so the twisted case. So this is, as I said, proposed by. So sigma is diagonal automorphism. Of G. So sigma to be R equal 1. Then I consider M Quiver variety. Of type ADE as usual. And so usually we consider the equivalent case really for the group G equal product of J and linear group for Ws. So I consider K of G times C star, which corresponds to quantum parameter, and MPW, and take direct sum. So in the usual setting, this realizes the representation of quantum. UQ of G1. Then new modification is, so you have this diagram automorphism, so you consider the product, semi-direct product with the finite cyclic group generated by sigma. Maybe this is. Then you find that this is too large, so you just tensor with representation ring of this finite cyclic group, and this is given by homomorphism is given by evaluation at sigma. So this is fine.
This can this be generalized to the case when sigma is the diagram automorphism of G1 rather than G more generally? Like
no. Then it becomes different. So the Quiver variety is defined based on the finite linking diagram of ADE. So it is not. I mean, if you go to the G of 1, then you get the quantum toroidal algebra. Then it will be another thing.
If you take twisted affine algebra, which is obtained from automorphism of the affine diagram. Instead of what you are doing is you affinize finite diagram. Like you have an automorphism of G, of Drinkin diagram of G. But what if you have automorphism of Drinkin diagram of G1? And
I still don't understand the question. So if I apply G1, then the Quiver variety is responsible for the representation of quantum toroidal algebra, not the quantum affine algebra.
Yeah, is this just the key figure of the fixed point set?
Huh? So this acts also on G. Fixed point set of.
Oh, okay.
I think it's slightly more complicated.
So are you saying that there should be also a twisting form corresponding to the automatic?
that's right. Yes. So there are not all twisted affine algebras are obtained in this way. There are some ones that are obtained right.
No. All twisted affine algebra is obtained from the diagonal automorphism of. You look at You start with the diagonal automorphism of K, not the K of 1. So that is the classification. And then you take the Lagrange DR, then you get untwisted of the type PCG, FG. So if you, and in fact this kind of construction, so consider the equivalent sheaves, and so this means you kill some sheaves, some representation which correspond to which vanish, whose character vanish at this point sigma. So this kind of construction appears in Lustig's works for canonical basis or symmetrizable. And also similar equivalent case study was used. This is one, and this is. Chris also studied affine Hecke using this Hecke case study. He analyzed Hecke algebra with unequal parameter. And this modification is slight, and almost all the machinery machineries which were used to analyze equivalent case theory are available in this setting also. And one also interesting remark is that this construction cannot be applied to equivalent homology. Maybe using equivalent homology groups, at least in naively. So if I use the local system corresponding to this finite group, maybe there might be some possibility, but at least for the usual one, usual homology group, and if you just consider equivalent homology with respect to finite group, then it contains no new information. So this construction and this part doesn't make sense. And also I realized that so. In the usual setting, if you replace the equivalent case by equivalent homology, then instead of quantum affine algebra, you get the Yangian. And so I recently realized that show that there is no Yangian for the twisted quantum affine algebra. So if you introduce a filtration and consider the associated gradient for twisted quantum affine algebra, then you just get the ordinary Yangian, not the new one. So I guess this should be compatible with this remark.
So I have a question. So if you consider, for example, the simplest twisted affine algebra, A12 with matrix 2 minus 1 minus 4 2. How is it obtained in this way?
What do you say?
A12 algebra. So
A12?
Yes.
Uh,
So it's like 2 minus 1 minus 4 2. So is it? I mean.
I don't A1 2. So this is anyway. So this should be. So you should start with A1 and my.
But it has no diagram automorphism.
Well, maybe then I'm not sure. So maybe the classification is. I just refer the classification in cuts.
But I think it should be just automorphism, not necessarily diagram automorphism. It could be an inner automorphism.
Inner automorphism. Then I'm not sure. I guess this is always a diagram automorphism, and I'm not sure inner automorphism. I cannot apply the construction because in Quiver varieties I don't have the real algebra a priori. So real algebra appears afterwards. So I really need the diagram automorphism.
You need that.
Yeah.
So this will not be all twisted.
Well, but I look at the cut. I mean, maybe I looked at the Cut's book again. But as far as I understand, all the twisted affine algebra appear in this way.
Why was construction I mean, why was construction be applied to learn homomorphism?
Well, if you just do naively apply the same kind of construction, then the point is equivalent homology of finite group after tensoring the complex question. This is just trivial.
Okay.
But this is representation theory of finite group. Or the case, this is the difference. Okay, so anyways, I'd like to finish this twisted part. And for one twist, I assume this is not of A to N. And so I mainly talked about, because the construction is most easily explained for quantized Coulomb branch, so I switched to from Quiver variety to Coulomb branch. So as I said, this is joint work with Alex Weekes. So I consider the case Bn of 1. So this is additional vertex, and I denote the symmetrizers to this is symmetrizers or length of the roots. Then I prepare two complex variables. G short and G long. Short and long. And they are related by this relation. G of S square or 3 or 4 or G2 is equal to G of L. So this I impose this relation. So I have a covering corresponding to the corresponding variables, 2 or 3 for the covering. Then, so I ignore those multiple edges and consider the Quiver of type A in this case. So this is extended vertex. So but I remember that there is this symmetrizers. Then I consider the corresponding Quiver gauge theory. So I is the vertex for this thinking diagonal type A, and W is similar. And then I consider the framed representation. So I choose some orientation. Then I define the modified version of variety of triple.
So what is the symmetrizer? Could you repeat?
So you have Cartan matrix, and then symmetric. So I consider the diagonal.
Oh, I see.
So it's length of simple roots. So this is a modular space of bundles. So this is EI. So for each vertex, so over the formal disk, spec of G of S or G of or L, according to the length of the roots. And Fleming, so this is trivialization of EIs over the, so I denote this by S or L. Here I consider punctual disk, and this is trivialized to the trivial one. Tensored with this vector space Vi. So EI has rank equal to dimension of Vi. And then, so n valid section. So I have corresponding arrow ij. I have a homomorphism Bij from EI to EJ, and also AI corresponding to Wi tensored of D of S. Such that they extend they are conjugate. Under this homomorphism phi, the only thing which you must be careful is that, so this EI and EJ, so for the most of the cases they live in the same disk, but for this this edge, EI and EJ lives in a different on the different disk. So in order to consider the homomorphism, so you must put So which is which? So this is longer, and this is long. This is short. So you have a homomorphism from G of S to G of L. So you must pushward. So you must push. So this modification is the new part, which in the original version of the variety which I considered with relevant. Think about was the case when all the disk is the same for arbitrary vertex, but here we take two different disks corresponding to short root and long root, and I consider the corresponding 2 or 3-fold covering.
So for each I, you choose either S or L?
Yeah, it depends. So this is two
according to
this rule. So in general, you have so short root and long root, and so this is twice was 3 length times length, half length. So and you impose the same relation, and you have two kinds of disks, and they are related by covering. And when I consider the homomorphism, I take the pushward. So basically, you so this is naively. So if in the original setting, maybe so G1 for the usual or the usual quantized Coulomb branch. So R is the modular space, or maybe R quotient by G product of G of VI. G moduli space of bundle plus sections over this raviola, this disk glued over the two disks glued over the punctual disk, and you trivialize one of the bundles. And this is also considered as a space of maps.
Excuse me, I didn't understand. So what is push for n-valued section? So you have n.
N is a space of homomorphism.
Ah.
So according to n, so I consider corresponding homomorphism. So in general, if you have G bundles and n is a representation of G, then I consider G bundle together with the sections of associated vector bundle. So this is the construction.
And what is this pi?
Pi is, so I denote GS and GL is related by this relation. This relation. According to this relation, I take.
Ah, yeah, okay.
Maps from this BR to the stack n divided by product of GLVI. So, but somehow for this new construction, so we consider we replace both target and domains. So because So for implicitly in this construction, I need to assume that the target space is just a single disk. But I consider two disks related by this covering. And also in the target space, maybe target is not really changed, but yeah. We replace also domain. So it is not simply the space of maps to a modified space. So this, I think, this is the one difficulty which I didn't see before. So I try to, so basically the cotangent bundle of this space is a Quiver variety. So I try to modify the target space, but somehow that is not the correct way to think about. So you consider instead the space of maps from this disk to target space, Quiver varieties, and then try to modify the space of maps.
So is that not the case that this is the that you take like equivalence map with respect to automotive over domain and target? Is that not the way it's
as far as I checked it, it seems this is yeah, you can play this game. It seems this is different from.
So that would be different.
Yeah, this seems to be different.
Just a second. So what you explained here on the left, is it related to GR or to LGR?
LGR. This is LGR.
And this thing here on the left also is related to LGR.
All this. So from here, so I consider LGR.
So there's no way you can explain by some kind of geometric picture what this conditions mean.
Well, this is a geometric picture, so.
So I think what one would want to say is that somehow you work at the variety with some kind of funny twist where, as you go around the origin of your ravioli, you add by auto.
Yeah, that is.
That's not the same.
Yeah,
That would sort of naturally impose this thing that you impose by hand, how to treat the long and short was different.
Well, I need to look at the, but then you also need to change the target space, right?
Yeah. So you add them both on the disk and the card, simultaneously.
Yeah, I need to check it again, but as far you suggested me some time ago, and I tried to check it, and I found slightly different, and yeah, I found it slightly different. So.
And so this ravioli is a non-separated scheme.
Non-separated scheme. So from here to here, I just trivialize the bundles on the lower.
And how is it used that this is GLR and rather?
Yeah, I will state the result.
Arbitrary, can you do this construction for any affine or even maybe?
Yeah, so this construction works for any Katsumudi.
So this can be in principle phrased for automorphism of arbitrary order. You don't need this.
No.
You don't need this quiver to be right?
No, arbitrary.
So you can define now this space of triples for any Katsumudi algebra, not necessarily simply related. Yes.
No, not necessarily. It's arbitrary. Symmetrizable. So I need to assume symmetrizable at least.
No, but what I'm trying to say, you start with like arbitrary equivalent.
You can have several rules.
Yeah, you can have some. Now you have a lot of work. But it still has to be your automorphism. Still has to be in just one automorphism, not a group of them.
A group of automorphisms? What it is? Group generated by automorphisms?
Okay.
So anyway, so on R you have the usual action of G, which is the product of GLBIs by change of S or L. Maybe slightly sloppy about this. So then I consider K, H star or K, G, or you consider the C star of rotation of R. So where C star of rotation acts by G of S.
Can I ask one more question?
Sure, sure.
So when you push forward onto this like a spherical cubic map, that means your rank kind of jump, right? That means you effectively, there's some sort of unfolding of your quiver happening. You have like a space twice the size. It's that, you had the same quiver, but you didn't unfold your quiver.
I didn't unfold the quiver.
You didn't unfold it. But is this unfolding somehow hidden in the fact that there is a push forward and for the rank?
Yeah, hidden. Yeah, it's hidden. Yes. And I think that this will disappear again when I consider the fixed concept, and that is the reason why the representation theories are related. So H star of G of R, if I don't put this rotation, loop rotation, so this is commutative. So this is a Coulomb branch, modified version of Coulomb branch. Of this case with symmetrizers. And for type ADE, this is isomorphic to so-called generalized slice of affine class money. Of type BCFG. So in the previous construction, we succeeded to construct slice in the affine class, general slice in the affine class for type AD, but this new construction gives BCFG. And in particular, if you consider the intersection hyperbolic restriction of intersection homology of this slice, then this realize representation of this real G of BCFG by geometric Satake. And as you pointed out, this construction makes sense for any symmetrizable Katsumudi. So we conjecture that this geometric Satake can be generalized to arbitrary symmetrizable Katsumudi. So this construction, this if you don't see this group rotation, we still have the maybe let me continue.
So what do you expect for arbitrary Katsumudi algebra? What kind of state?
So we have this is commutative, this is true, and we have some space, and we consider the hyperbolic restriction of intersection homology complex. This realizes integrable highest weight representation of Katsumudi real algebra. This is the expectation.
Well, they say,
maybe I didn't specify. So this is, I started with V and W, then this can be, W can be changed to two weight pairs of dominant weight and weight which is smaller than lambda. So this is representation highest weight space, mu space in the highest weight lambda representation.
But there you really have CBFG, right? It's not BCFG.
CB.
There's a Laplace dual in there, right?
Well, that depends on the construction. I think that I started with this linking diagram and I specified the symmetrizer, then BCFG. I think it depends on how you start.
No, but just if you get slice for BC, then you get representation of CB.
Sorry. That's the point. I see. Maybe I. Yeah, I understand. Thanks. So this is isomorphic to truncated shifted Yangian. of type BCFG. And we don't check the corresponding statement for K-theory. And this is truncated shifted quantum affine algebra. For G of R of L. So then maybe I running out of the time. So as I said, so I can use the machinery for the analysis of the convolution algebra developed by Ginsburg to apply this setting. So apply. So then, so I ended up with understanding of this kind of variety. So I have T. Maybe I forget to introduce variety T. So T is the same as R, but without extension condition. And then you have a map to n of k, so this k valued, n valued k point. Trivial bundle. Over the disk. And then, so this you consider the infinite dimensional variety n of k of t, and then consider some fixed point in one parameter subgroup acting on basically this one parameter subgroup is basically this is C star to product of general. Then you just study the fixed point, and this you find that this is just easy computation. This is the variety appeared in Lustig's works on work on K canonical basis. So this is type AD. So even if you start with this modified construction, so I take this 2 or 3 fold covering, but once you study this fixed point, then you end up, so this somehow covering is unfolded in this taking the fixed point, and you get this AD linking diagram. So it means you start with the ordinary setting and twisted one, in the fixed point, you get the same variety at the end. So that is the reason why you get the relation between the representation of the two different algebras. That is my proposal. So thank you for your attention. I stop here.
Any questions or comments?
Yes.
Do you have this monopole generator formulas for? Do you have the monopole generator formulas?
Yeah. So most of the things which we proved for the ordinary Coulomb branch remains to be true in this. I mean, this is really slight modification, and most of the things which I think that most of the things are generalized, and so far I don't know anything which cannot be generalized. Yes?
Is there some relationship between the two approaches, the Coulomb branch and the fixed branch?
That is, well, Yeah, that is part of ongoing work with Andre. So, as I said, this Coulomb branch is based on the space of maps from the disk to this ravioli to the quotient stack. And in general, you can consider the space of maps from P1 to Quiver varieties. And then on this equivalent case theory, you have an action of this shifted quantum affine algebra. So that is, I think, the unified. And this construction should be modified to this kind of setting, modifying the domain. So once this generalization has been done, then somehow I mean, both the ordinary Quiver varieties and this variety of trips are set in the same footings, and both could be viewed in unified way.
Here you were covering the whole algebra, right? Before you were expecting this subcategory.
Yeah, this at that point I still don't study it carefully. Maybe I didn't. So even in this case, when applied this analysis of the convolution algebra, I need to specify certain subclass of the representation, which is I think more general than the finite dimensional ones. So it in particular includes infinite dimensional representation. But so there's a commutative subalgebra in this Coulomb branch, which gives the integrable system, and I assume that the representation which decompose into generalized eigenspaces with respect to this commutative subalgebra. So this is some restriction on the category of representation. Yes.
So when you consider Youngians of non-simply Lie algebras, there are actually two things you can do. So one thing is just take the Drinfeld Youngian, and the other thing that you can take, like for BC, you can take this Alshansky Youngian, which is a twisted Youngian. And so which of the Youngians do you get?
Drinfeld Youngian. Drinfeld Youngian. So this
twisted Youngian appear also.
Twisted Youngian, I guess this is you should start with some different geometry. Not
I mean, they're not Hopf algebras; they are co-ideals.
Yeah, I know.
So
yes.
And do they appear also? The geometric treatment of them?
Yeah, that is not my expectation. Maybe some others. So people consider the, for example, cotangent bundle flag variety of classical types. Then this is not the Quiver variety. The cotangent bundle flag variety of type A is an example of Quiver variety. But if you consider the cotangent bundle flag variety of classical groups, in general, they are not Quiver variety. They are also the Coulomb branch of some different type of gauge series. So it's interesting to explore this construction, but this is something different from this story.
And can you explain the relation to KLR algebras? So is that visible?
So if you so this fixed point basically, so this convolution algebra of this variety is KLR. But somehow the relation with, I mean, at least in the level of convolutional algebra, the variety of triple is very much similar to the variety which Lustig used for the canonical basis. So I replace the vector space by the modules over the formal power series, and I consider instead of linear maps, I consider the homomorphism over the formal power series. So KLR algebra is our variety of trips is kind of infinite dimensional version of KLR algebra. But once you consider the loop, the one parameter subgroup, and take fixed point, then basically it means instead of how to say the formal power series in the linear maps, I just take a constant part. So I go back to the original situation which Lustig considered. So that is the mechanism which I get basically KLR algebras, this kind of analysis.
Any other questions? No, let's think. we resume at 11. And there's a coffee break 1 floor up. So you should.
Here, you want to introduce the question on the circle.
So I think to get all of this, find out, allow